And here we go. All right. This would be our fourth lecture, I think, which is more about chapter 2. So we've got our spectrum of looking at data. Here we have high detail, slow understanding, which is generally looking at the raw data. Over here we have low detail and fast speed of understanding. And by that, I don't mean you understand everything about the data, but it gives you an insight into the system, right? Is it a population? Is it some other system, right? A single piece like the most common observation. That gives you a real fast insight. And then in the middle, we have, so low detail, fast understanding are going to be our summary statistics. And in the middle are various kinds of visuals. Now with categorical data, qualitative data, after looking at some raw data, we made two kinds of visuals. We made frequency tables and bar graphs, or bar plots, or bar charts. And then we looked at basically the two summary stats that we would care about, which is a proportion if it's binary data, and a mode if it's got a bunch of different categories. Today we're going to talk about quantitative or numerical data. Let's see. Here's how I want to do this. Chapter 2, I believe, is going to ask you to do some of that. So let me use this as an example. Here's one. I'm not a big fan of IQ scores. Those are a real old system of measuring something that doesn't necessarily map onto success, let alone happiness and health. But it is something that can be measured, so statisticians sure did like measuring it and still do like measuring it. There's our raw data. What's the highest IQ score? Okay, it took 9 seconds to get there. I think that's right. Oh, 118. So it took 12 seconds to get there, and there was something that was wrong. Right. 119 took 15 seconds together, and we got it wrong twice. Right. It takes a while to get an understanding of your system when you're looking at the raw data. So instead, let's look at this using a visual. And I'm actually going to show you how to do this using R so that you don't have to do it all by hand. This will be a benefit for you when you go and actually do your homework. I'm just setting up a little R script here. So here's my R script, my R window. All right, nothing lives there yet. I wouldn't recommend using your lab script for this, but you can always just create a new script and then do that work in there. And if I'm going to work on this, I need to get the data in there. And you might say, gosh, I don't remember how to get the data in there. And then you remember that your instructor helpfully gave you the sample commands for homework, which starts off with to enter data. This is how you enter data. So let's copy this in. There is a lot of copying and pasting in coding in general, and especially when you learn to code. Maybe not as much this days with AI coders, but in the days that I did it, huge amount of copy, modify, run and test, and it doesn't work, and modify until it works. So it's not wrong to copy code. If you use a lot of code from another source, it's a good thing to cite it, but it's never wrong to use code. So this is how I would do data in general. And of course, now that it's here, to get R to know about it, I click run. I have a lot of stuff in there, but I should also have data right there. 1, 2, 3, 4, 5, 6, 7. Of course, that's not the data that I wanted. I wanted this data. So it's time to modify. You can just copy all of it. And notice to put data in like what's called a vector, a list of values. We start with the C. I don't know why it's the letter C, but it is. And then a parentheses. And then every value needs to be separated with a comma. That's not going to happen when I paste this in. It's just going to give me a list of numbers. So I have to do a little bit of work, but it's not too bad, especially if you do it a lot like I do. You can just, I'm pressing comma and then I'm going over. And you can watch me do it and you can get bored if you want. Every single, additional observation. 2 commas is going to cause an error. Needs a comma after it. This is pretty slow, but I tell you, it's a lot faster than doing it with the hand calculator. The only thing when you're entering data is the very last one is the very last one. So it doesn't need a comma after it. And there's my parentheses closing everything. If you want to be safe, highlight all of it and then run it. And now there's my data. Now it's in R, and now I can work with it in R a little more easily. Okay. So that might be your first step, is let's get our raw data into a system where it's going to be easier to look at it more quickly. So hop back over to the notes real quick, and then we'll come back to R. We'll start with visuals. 2 main types of visuals for looking at a single quantitative variable. There are others. These 2 are enough to encompass most of what we would ever care about as a statistician. The first one is called a histogram. This is one of the heavy lifters of visual data analysis in statistics, is a histogram. This is basically a bar graph where the bars represent ranges of values. So we kind of build ourselves a frequency table. You can look at a frequency table for quantitative data if you prefer looking at numbers, but we already dove deep into that with the qualitative data. So I'm not going to look too much into that. So what we're going to do is we're going to build ourselves, lay ourselves out the space we need to make a bar graph. And instead of having categories like black, red, blue, and green, we're going to have ranges for data. So we're going to start here with whatever the smallest observation is. And then we're going to give ourselves some different ranges until we get up to where the largest ranges are. All right, so we need the smallest value. What's the smallest value here? The correct answer is, come on, I'm not going to do it that way. I went all of this trouble getting it into R. I'm just going to use R. You want to find the smallest value in a list of values, you just ask it for the minimum, and then it tells you 85. I'll zoom in a little bit. Hopefully we can still see everything. I know folks who are far away, it's hard to see. All right, so by the way, a minimum is also a sample statistic or summary statistic, because now we know something about our data. We know the smallest it can be. Let's see if 119 was actually the largest. Oops. Yep, 119 was the largest. So over here in our histogram, let's start at 85. Now we need to pick how wide each of these classes should be. The width of the range of values is called a class or a bin or a bucket. You'll see it in different ways. I think in this course, we use the word class. As with everything in statistics, or many things in statistics, it's kind of a human decision, but I probably wouldn't want 3.7 as a class width. That makes no sense. I probably wouldn't want 20 as a class width. That's probably too big. So depending on your data, you might pick 1, you might pick 2, you might pick 5, you might pick 10, you might pick 20. In this case, the homework and kind of looking at that range suggests that if we have a class width of about 5, that might make some sense. Let's see if I did pretty good. There we go. All right, so 85 up to 120. There's not any observations more than 120, so I'll stop at 120. And now we have to go through and we have to count how many observations are between 85 and 90. Before we do that, do we think we should put 90 on the left side or 90 on the right side? All right, if I have an IQ score that's exactly 90, should it go in this bar or should it go in that bar? Talk to your neighbor and decide where do you want to put it. I'll give you a little time to talk. Francis, what did you say?
On the right side, right up against where the line is for 90, not below 90, because from 85 to 90, let's say below 90, but by having it right up against the line, that would say that it's at least 90.
I think that makes sense. Did anybody say they would put it down here in the 85 to 90? The thing that I heard that I really liked was my brain could convince me either one could be right. This is a human decision. As long as you pick something and stick with it, you're going to be fine. Most statisticians would say anything up to but not including 90 goes to the left. 90 or more goes to the right. But there are books and maybe a couple, out there statisticians, maybe they're left-handed, I don't know, who would put 90 on the left side. So make a decision, stick with it. Your visual will still give you good information. You just don't want to put it in both places. So we come back to our data. All right, now we have to scan and say, all right, what about everything between 85 and 90? So I've got 1, 2, 3, 4. I see 4. Anybody see more than 4? Okay, I see 4. So we make a bar that's 4 high. That kind of implies what our scale can be. And, it doesn't hurt to put the label on top. I might have to extend vertically. We'll find out. One difference between a bar graph and a histogram is usually we separate bars with a little space because black is not really right next to blue. But histograms, we're not going to separate it because 89.99 is right next to 90. And then we do it again with 90 to 95, right? And 95 up to 100, but not including 100. As with many things with data, it gets exhausting if you try to do it all by hand. So we can make our work a little bit easier and look at it sorted. Now, yep, there's 4 right there. And then 1, 2, 3, 4, 5, 6, 7, 8 right there. So our next bar should be 8 high. 1, 2, 3, 4, 5, 6, 7 for our next bar, etc., etc. So let's do this once by hand. What I'm going to do is I'm going to pull this over to my other screen. You won't see it, but that's okay. I can tell you that there are 8 of them in our next bucket. And then there were 7 of them between 95 and up to, but not including 100. One, two, three, 4, 5, 6, 7, 8. There were 8 of them between 100 and up to, but not including 105. 1, 2, 3, 4, 5, 6, 7. Another 7. Between 105 and up to, not including 110. Another 8 here. And finally, 8 here. Because these homeworks are generated algorithmically, when you go to it, you might see the numbers are different. But this is how it turned out for us. I think part of this homework question, let's see. Yeah. Part of this homework question, because it's hard to ask you to make a histogram in the online homeworks, but it asks you to pick a histogram. Now, do you see the histogram that matches pretty closely? It's this one. They used a different scale. They used 84.5 up to 89.5. Fine, they were consistent. Here, not with here. I appreciate the person who wrote the homework questions, but I would say that's a difference that I take a little issue with. Of course, we've got R, might as well make it here. All you have to do is type in hist. I better change my window a little bit so we can see what shows up. If you run a histogram of the data, there it goes. This one happened to pick classes that were spaced 5. R will kind of pick them based on its best judgment to help with a fast interpretation. You can force it to have more or less. I think I can make it have the number of bins. Right now there are 8. I think I can make it have 10 bins. No, I didn't like that. Let's try 12. Didn't like that. All right, it doesn't necessarily list. If it thinks it's a really bad idea, it's going to ignore you. And apparently it's thinking all of these are really bad ideas. Can I get it to do 7? Oh, well. Oh, it did 7 here. Did it do 7? No. 1, 2, 3, 4. Yeah, that's 7 now. And then was 8 different? No, it was just 7 and it's not going to let me change it. So the one thing about R is if you're using R to try to match with the homework, with the histogram, it might not match exactly, but it's still going to be pretty close. Okay, so that's our first visual, which is a histogram. Tell me more or less what's the minimum observation? 85. I mean, you knew that already, but still that's a pretty fast response. Maximum observation, more or less, from this picture, 120. We know it's actually 119, so that we lost a little detail, but we still got close. What's roughly the center of this data? Go ahead, Ashwin. Yeah, right, kind of in the center. Like if you took your pen and tried to balance it, I would put my pen here. If you're thinking about half the data being less and half the data being more, this roughly splits it down the middle. Right? Not easy to tell from the raw data, but from the visual is very quick. So now we know roughly where the span is and where the center is. Let's talk more about the summary statistics, and then we'll come back to the second visual later. So key summary statistics for quantitative or numerical data. Well, probably the most important is measuring the center. So a measure of the center. And there are two that we consider. Right, knowing the center of data is really valuable because that, more than anything else, tells you roughly where that data lives, and it gives you an idea for the observation you would most expect to find. Right, so this is the most likely observation. It's not always the center, but it usually is. And so our first measure of the center is called the mean, which really means the average. I'm going to use the word average more often than I use the word mean because in English, mean means signify, and mean also means average, and it can be really confusing. In Spanish, it's the promedio, which is nice because promedio and significar are very different. But in English, it's an issue. So the mean is the average. And to calculate it, you add all the observations, and then divide by the number of observations. Do an example. Let's have our data be 1, 3, 4, 5, 6, 9, and 10. I went ahead and did it in order just to make things a little easier. Doesn't always come in order. So the mean or the average would be 1 plus 3 plus 4 plus 5 plus 6 plus 9 plus 10. And then you divide by 1, 2, 3, 4, 5, 6, 7. There were 7 observations. So you divide by 7. Let me do that real quick. I'm just over here in R using it as a calculator. Oops, tried to. So that's 38 divided by 7. Which is 5.43. Now, technically, it's 5.428571, et cetera, but how many decimals do we really need, right? If you're measuring precipitation in millimeters, you probably don't need 6 decimals for precipitation. If you're measuring blood pressure, you might not even need any decimals for measuring blood pressure. You might toss 1 in there just so it's a little more clear that it was a calculation and not just a number you picked out of the top of your head. And notice that 5.43 is close to the middle of all of these numbers. And so if I said, if I grabbed a number at random, what's my best guess for what it would be? You'd say, I don't know, something in the neighborhood of 5 to 6. And that's kind of reasonable. All right, so there's another measure of center, which is called the median. And I usually refer to this as the actual center of the data. It is the central value or the middle value. To find the median, you just find the central value. So usually order the data smallest to largest. And then count in from both sides. Let's use our same data as our example. So I'm going to order it from smallest to largest. And then I actually do this, and I actually recommend you do this. I take my fingers and I count in from both sides until my fingers meet. That works. Maybe it's not necessary with just 7 data points, but if you have like 23 or 32 or something like that, it can help to count in with your fingers instead of just eyeballing it. So the median of this data is 5. And again, that's pretty central. Both the mean and the median can be useful. The mean is more often used when we do mathematical statistics. We're going to be using it a lot in the second half of the class as a way to understand when groups of observations are surprising. The median is nice because it works when you have data that doesn't behave in a very well ordered way. When you have crazy data, the median kind of ignores how weird it is and just finds the center. I'll get into that a little bit more later once we talk about our other summary statistics. I don't want to add up 50 observations by hand here. But I don't have to because R calculates the mean. Come on. This means my window is too small. There it goes. 103, right? Which is roughly what we said, right? The center looked like it was between around 100 and 105. And the median, oh, also 103. Yeah. So let's go back and open this picture a little bit more. All right, there's a center of our data. Whether you talk about it as the median or the mean, they're both pretty close. Visually, the mean, the average is if you balanced this whole data on the tip of the pen, where would that balance point be? And the median is simply if you divided it in half, where would the dividing line be? So let me show you an example where the mean and the median are not the same. So what I'm doing right now is I'm generating some data. I'm going to generate, let's do 1,000 observations. And then let's take a look at it. So this is completely valid data. I mean, I could probably think of something where you have a lot of observations that are very small and then some observations that are surprisingly big. Maybe not on this scale, but cakes, right? Most cakes are pretty small, but every so often someone tries to make a giant cake. Now, the balance point of this is going to be somewhere out here because we've got some observations way out to the right. It's 1.14. And the median is 0.5, right? So they're both kind of close to the side, but they aren't as close to each other as you might expect. I just kind of came up with this off the top of my head. If I wanted to really force it, I could do something like add in what are called outliers. Outliers are data that is surprising to see. So let's take a look. Let's add a bunch more observations up at 14. All right, so these are outliers. So I don't know, there's some party going on and some people are making some really big cakes. That pulls the mean up from 1.1 to 2.3, and it's hardly going to change the median at all, just a little bit. All right, and I can really make it crazy if I did this, and let's add an observation in at 50, just for fun. All right, the mean continues getting bigger, and the median hardly changes at all. So means and medians don't necessarily tell you the same information, but they tend to be very similar. Okay. All right, so those are our measures of center. The other thing when you look at a histogram, for example, is you want to know how spread out the data is. So in addition to have measure the center, we also have measures of spread, which is sometimes called variability. And there's a measure of spread that goes along with the mean and a measure of spread that goes along with the median. The mean is paired with something called the standard deviation. The standard deviation is a single number that describes how spread out the data is around the mean. Standard deviation is often abbreviated. I will often abbreviate it as STDEV. Sometimes it's abbreviated as SD, and that's how you put it into R, but I think that's a little bit too vague, so I'll stick with STDEV as a standard deviation. Calculating the standard deviation is the most laborious calculation. Maybe not in all of statistics, but definitely in the type of statistics we're doing, which is descriptive statistics. You will do this by hand once on your homework, and you will never do this by hand again. I will walk you through the steps because there's a logic behind the steps that I think is really valuable to understand. We're going to do a really simple data set. Our data is going to be 1, 3, and 4. So here we go for calculating standard deviation. Step 1, calculate the mean. 1 plus 3 plus 4, all divided by 3. is 8/3, which I can write as close to 2.67. Close enough. That makes sense, right? That's kind of in the center of 1, 3, and 4. It doesn't match any of the observations perfectly, but that's okay. Now we want to figure out how far is every observation from the mean. That's pretty easy to do. Mathematically, how do we find distance between two numbers? Subtract them. Yeah. So we'll take our first observation, 1, and we'll subtract the mean. 1 minus 2.67 is negative 1.67. And 3 minus 2.67 is 0.33. And 4 minus 2.67 is 1.33. It's not so bad when you only have 3 observations, but you wouldn't want to do this by hand for 100 observations. Now, there's kind of an issue here. Let me draw a picture. I like pictures. Here's our mean at 2.67. And here's our observation at 1. And here's our observation at 3. And here's our observation at 4. So I've got my distances, but one of those distances is a negative number. And distance shouldn't be negative. Distance should always be positive. So mathematically, how do we make sure that a number is positive? We square it, exactly. You could take the absolute value, but squaring is easier. Also, it has an additional benefit in that it penalizes farther observations more than it penalizes close observations because it stretches that number out. So we just want to make each of these distances positive. Make each distance positive by squaring them. So we take negative 1.67 and we square it. We take 0.33 and we square it. And we take 1.33 and we square it. I'm going to have R help me with that. So I get 2.79 and I get 0.109. Probably could have done 0.011 and 1.77. That's good, but that's not a single number. That's 3 numbers. And I only have 3 observations. The whole point of summary statistics is have to have just one number if you can. There's an easy thing to do. We can just add all these up. That'll give me a single number. We add up all the squared distances. So that's step 4. Add up the squared distances. So 2.79 plus 0.109 plus 1.77 is about 4.67. Now I have a single number that describes the spread. But the problem with this is I had 3 observations. If I had 10 observations, this number would be bigger, even if they were close, right? Because I'm just adding more positive numbers. So really, I want to adjust this. I want to, what's the word I'm looking for? Scale? No. Balance? Scale is not the word. I can't think of it. Average it. Yeah, I want to average it. Average this sum of squared distances, that's what that 4.67 is, by the number of observations. So I take 4.67. Oh, it turns out mathematically, it was a little better if you take one away from it. I don't know why. I kind of know why. So we're going to divide 4.67, not by 3, but by 3 minus 1. If you have 100 observations, it doesn't matter so much. So 4.67 over 2, 2.335. We're almost done. One more step. We have this 2.335, but that came from squaring distances. So we want to undo that squaring. And we can undo that squaring just by taking the square root. So we'll take the square root of that number. Plus square root of 2.5. The standard deviation is, let me do this first. Square root of 2.335 equals approximately 1.53. The standard deviation of that data is 1.53. So here's my data. On the number line, I have 1, 3, 4. The average is here. And the standard deviation, 1.53 is reasonable in either direction. That's kind of the idea for the standard deviation is what's reasonable? Yeah, anything within one standard deviation is super reasonable. In fact, anything within 2 standard deviations is statistically, it's not surprising. And it turns out that 2 standard deviations is one of the most important concepts in statistics. So knowing what the standard deviation tells you is very important. We get it by finding the center or finding the average, figuring out how far each observation is from the average and making that distance positive, adding up all those squared distances, dividing by the number of observations so we can standardize. That's the word I wanted, standardize. So it's called a standard deviation. And then we square root to get back to normal distances instead of squared distances. Let me show you the homework question where you get to do that by hand. Unless I took it off. No, here it is. First, you calculate the mean. Then you find the distances between your observations and the mean. Then you square all of those. Then you add them all up. Then you take the square root, and that is your standard deviation. I will spend some time, if not today, then next Tuesday, talking about all the different symbols that statisticians use for all of these, which I wouldn't necessarily use for a couple of reasons. One, I don't think it's necessary. And the other thing is there's no fancy Greek letters in R. You can't put a Greek letter into R. You can only use basic Latin letters. Let me pause the video for a second. All right, I'll stop the video now, and I'm going to upload another Chapter 2 lecture video next week.